Kirigami extends origami by introducing cuts into flat sheets. These cuts are placed locally, leaving small, uncut regions that act as hinges. The resulting kirigami structure is deployable if the faces can rotate without deformation, and uniformly deployable if all hinges open by the same angle during deployment. Hinge kirigami structures are fully characterized by their topology and geometry. A well-designed hinged kirigami structure requires both good topology and good geometry to exhibit auxetic behavior during deployment. In contrast, poor topology or geometry can result in a useless structure, or even one that is impossible to deploy. We use a 2D disk topology mesh to represent the exact shapes of the faces in the kirigami structure. We then use face orientations to specify how the faces are connected after cutting. Faces assigned a clockwise orientation are colored blue, and those with a counterclockwise orientation are colored pink. If two adjacent faces have the same orientation, meaning they have the same color, they are fully separated after cutting. We refer to this as a split cut. If two adjacent faces have opposite orientations, the directions along their shared edge agree. After cutting, a hinge vertex is created at the source vertex of the shared edge, while the other endpoint is split. We refer to this as a hinge cut. Applying these split and hinge cuts to all pairs of adjacent faces produces a hinged kirigami structure. In other words, a hinged kirigami structure can be equivalently encoded in the original uncut 2D mesh, with the embedding X specifying the geometry and the face orientation sigma specifying the topology of the kirigami structure. With these definitions in place, we can pose the fundamental question: how can we find embeddings and topologies that produce uniformly deployable kirigami structures? Moreover, what is the space and degree of freedom of these admissible embeddings? Previous works have tackled parts of this problem. Quadrilateral kirigami patterns have well understood geometric constraints for deployability, which have been extended to high genus settings and spherical embeddings. More recently, deployability constraints have been generalized to kirigami patterns derived from periodic two-colorable planar tilings. This framework can check if a given tiling admits a deployable kirigami structure, but it does not characterize the full space of deployable patterns. In this work, we present a unified and analytic framework for exploring the design space of uniformly deployable kirigami structures derived from arbitrary planar graphs. Our approach can handle tilings that are not periodic or not too colorable. Our formulation allows us to explore different topologies of a kirigami structure derived from the same tiling. Here, we click on a face to flip its orientation. The resulting kirigami structure updates the geometry to adapt to the new topology, revealing different deployment behaviors. Our geometric constraints for uniform deployability can be expressed as a linear system, allowing us to linearly parameterize the entire design space and explore it seamlessly. By adjusting the coefficients of the basis vectors, the kirigami structure transforms its geometry while staying uniformly deployable. By characterizing the full design space, we can experiment with pattern shape optimization under different objectives. For example, if a pattern is initially non-deployable, we can find the closest design that is uniformly deployable. Here is another example showing a non-periodic pattern. We can also optimize patterns within the shape space to achieve conformal deployment behavior. The green circle highlights the linear transformation of the tiling during deployment. After optimization, the green circle scales without deforming, indicating a conformal deployment. It is possible to optimize some of the patterns to produce a fully closed tiling in their maximum deployable configuration. Since the paths connecting the hinge vertices do not affect the uniform deployability, we can add curved cuts to stylize the kirigami patterns. Thank you for your attention. Please see our paper for more details.